So we'll see how that comes out. Very quickly, hopefully the parts that gave you trouble in there was the factoring and the being okay with the x going away when you're solving equations, that kind of thing. Hopefully the like terms stuff didn't bother you, right? But, you know, what makes something like terms? If I have this... Are there any like terms up there that I can put together? No. I like it. There are like terms. With this first guy, there are 5 of these things. And what do these things look like? What are they made of? 1A and 2 B's. Are there anything else that has 1A and 2 B's? Yes. Yes. What did I do here? I just wrote them out of order, right? Alphabetical order is the accepted conventional way to do things. And I had a student that would just deny, they're like, it's different. But it's sort of like saying, is 4 times 6 different from 6 times 4? Of course not. They're both 24. I just chose to write them in different ways. So this is the same thing as that. So if I have 5 of them plus 4 of them, I got 9 of right? And then and this poor little dude has nobody to go with, and this poor little dude has nobody to go with. You kind of with me? Now, the idea of like terms is kind of cool. You can extend it to something else that people have a lot of trouble with, which is fractions. If I have 4/5 minus 1/5, that's easy because they're like terms. When I add or subtract, I require like terms. So if I look at denominators, 4 of these minus 1 of these is 3 of these. Yay, Jeff. But if I have 4 of these minus 1 of those, oh shit. Don't make it become 3 over negative 5. You guys see where that answer comes from? What did that person do? Yeah, 4 minus 1 is 3, 5 minus 10 is negative 5. What's the next problem, Jeff? Right. That sucks. You can't subtract them unless they're like terms. You guys get what I'm trying to do? This is a good explanation of why you need LCD for fractions, because you've got to make them like terms. We know you need like terms to add and subtract. All right, good. Apply it here. So how do you make this like terms? Yeah, times 2. So I got 8/10 minus 1/10. Now it's 7/10. Yeah, 8 of these minus 1 of the same thing is 7 of those things. I like it. Cool? Every now and again I'll get somebody, you know, it's the difference between this and this. Which one of those can you do? That's a times, by the way. Which one of those can you do? The top one or the bottom one?
The second one.
Second one, I like it. Right? Top one you can't do. X plus x squared. You don't have an x cubed. You don't have any x cubes. How the hell? So sometimes I get somebody tell me, oh, that's 2x cubed. Where'd you get 2x cubes from? I got an x and an x squared. And suddenly you're like, wow, there it is, 2x cubed. No, no. So no good. This is not like terms. You can't do a damn thing with that, simplification-wise. Here, x times x squared, they don't have to be like terms. They just have to be like bases, right? X squared means x times x. You put another link on the chain. So now I've got x cubed. Cool. All right, I like it. So when you multiply fractions, do you need like terms? Do you need like denominators? When you add, subtract variables, you need like terms. So when I multiply, do I need like terms? No. X and x squared, I can actually multiply those. So when I multiply fractions, those do not have the same denominator, but I don't care. I don't need like terms when I multiply. What does that become? I like it. I always get somebody to cross multiply there. It sucks. The minute cross multiplication is learned, you guys do it everywhere except where you're supposed to. The one place you cross multiply, you know, something like that. Then you cross multiply. Right? Even cross multiplication here would be kind of silly. But still, this is the one kind of thing where you can definitely just cross multiply. You can actually use cross multiplication in other places, but you have to be very smart about what actually happens. Here's the one place you can just not even think about it, just bang, Here I just multiply as it comes. Cool. I've gone off script here. Oh. Which one of these is associative? Oh boy. And which one is commutative? I always love that question, don't you? You guys remember those? Associative and commutative? Does that sound at all familiar? Sounds a little bit familiar? These are properties of addition and multiplication. They really just say I can multiply or add whatever order I want to. 4 plus 7 is the same thing as 7 plus 4. One of these is associative, one's commutative. So what did you guys do today to get here? You commuted. All of us as individuals commuted to get here. So individual things commute. Parentheses get up and associate with other things. So which one did the parentheses move? The top one. So this is associative. This is commutative. And I love it whenever you guys write the answer, you always make this like a commune, commutative. There's no N and there's a T. But I'm not an English teacher. I'll just make it a T. I'm not going to take points off, but just be careful. And this becomes really important and a little bit higher mathematics, because there are certain systems you can put together that aren't associative or commutative. So it becomes a question of when is it. But our normal real number system is associative and commutative for which operations? Let me say all that again. No, just part of it. Which operations does this work for? Obviously addition. There's only one other operation this works for. Multiplication. Right. So if I do 2 times 4 times 3, that's the same thing as 2 times 3 times 4. But if I do 2 divided by 4 divided by 3, I don't get the same thing. When I do it like that, I don't. And one reason you can see why that is because here the 4 is over the 3, but here the 3 is over the 4. So it's going to be two different numbers, right? Sure, like 7 minus 3 is not the same thing as 3 minus 7. You guys kind of... I'm not really... I have to teach you about these, but I'm not so worried about the words as I am about can you just do the work. Yeah. Okay. And then you got the distributive property, which we all should be pretty good with. But why does it work? It should kind of bother you. Order operations tells us, and order operations again is please excuse my dumbass son, or dear Aunt Sally, whichever one sticks in the head. But why does that work? Order operations says you're screwed. Can you do the inside? No, x plus 4, what is that? Pineapple? What is that? I don't know what the hell it is. So why suddenly can you break order operations? This should be a place where you go, Jeff, explain that shit to me, because you're telling me two different things here, right? And here's why this works. What really is 3x? What is that really? Don't say 3 times x. What really 3, what's doing what? What's 3x really mean? Isn't that x plus x plus x? Isn't that 3x? So a coefficient means that many of these adding. So how could I rewrite this? X plus 4 plus x plus 4 plus x plus 4, right? You with me? Because I have 3 of these adding. That's the definition of multiplication. I have 3 of these adding. And then I can just use commutativity and associativity and all that kind of shit and just say I can add whatever order I want to. So what's x plus x plus x? 3x. What's 4 plus 4 plus 4? 12. And so the shortcut, don't do that crazy thing. Shortcut is just distribute. That's the kind of thing that you should be a little bit like, why? And don't go, oh, just because they said so. And then that starts to build up. All of math is a bunch of bullshit they just make up on the spot. I mean, it kind of builds into that idea. When every damn thing, and it must make sense. It must, or else you got to throw the whole damn thing out. So I can't blame students for feeling like, why do I learn this shit? I'm never going to use it. I don't need it when I go to the grocery store. I love that one, by the way. You need to know how to do a lot of other things, whatever. But that's something you should ask about. That's something you should say, why the hell does it work like that? Okay. We all know that something times 0 is 0. What about that? Yeah, undefined. Anybody else call it something else besides that damn problem? No? Okay. Why is that undefined? Think about what that means. That means that there's nothing defined to be that. That's undefined. What does that really mean? So, what's 6 divided by 2?
3.
Why? Because 2 times 3 is 6. So whatever number I put here has to be the number that's defined as the thing that multiplies me this to get this. Well, what multiplies me 0 to get 6? Is anything defined to do that? So it's undefined. I mean, this is the kind of thing. It just gets to me that so many people throw math away, and this is why they do it. And I can't blame them if they just kind of accept this kind of thing, and they're like, all right, that's bullshit, but that's what they said. Okay, that's bullshit, but that's what they said. You know, and then it builds up, and you're like sitting on a pile of bullshit. I can understand why that would get to you after a while, right? But it's not. Okay. Very preachy today, so I apologize. In the white book, section 9.2 is about solving equations. In the blue book, I can't remember now what it was. I think it's chapter 4, chapter 3. But on your homework sheet, it should go right along. But the basics of solving equations, this is what I tell my Math 88 students. I want them to know when they come out of that class. So in this class, 103, I'm going to expect everybody to be really pretty good at solving equations. That's like your bread and butter skill, right? Word problems are difficult. What's the last thing you got to do in a word problem? Solve an equation. That part better not be the hard part, because the first part's hard enough already, right? What's something? So there's a little problem on there about something like this. Well, let's do this. Okay, if I had a problem like this, so I want to jump to the problem that gave us some trouble on the little warm-up sheet. If I start to work this out, right? So distribution always frees my stuff up so they're able to move. So now I always get something like this. I always get somebody who does this. And I understand why. Because you don't want the x to go away because you're like, it's in your head, got to solve for x, got to solve for x. But let it go away. 2x minus 2x is 0. There are no x's left. Is that a true statement?
No.
No. So there's no solution. What should twice x plus 1 equal? 2x plus 2. So it's a bogus problem to begin with. This is actually very true to life. If my boss came to me and said, Johnson, figure out how we can make $18 billion next year. No. Last year we made $3, so I don't think we can do it, sir. So you start with a bogus assumption. You're going to end up, math is going to go, if you can write that, I can write this. Nah. And we go, oh shit, that means I started with a bogus thing. There's no solution. So what does it mean then if I get, if I have the correct thing from the beginning, then I subtract 2x, and I let them go away. 2 equals 2. Well, that's true. So no matter what x is, this equation is true. So what's the answer then? What does x need to be to make it true? No matter what x is, this is true. So what can x be to make this true? Anything.
Real numbers.
Any real number. All real numbers. I like it. All real numbers are the answer. Does it require x to be something specific to make this true? No. Twice x plus 1 is 2x plus 2. Do I care what x is? No. That's the definition of freaking distributive property, right? So that's why this doesn't require x to be something specific. If I have a normal equation, like x plus 7 equals 2x minus 9. Right? There's a good normal equation, right? How do I solve that?
X minus
right.
2x.
Okay, I'm with you. So let's see. I can subtract 2x
from both sides.
So that goes away. Here I get negative x. Good. The plus 7 is still there. Equals
minus 9. Minus 9 from both sides.
No, 7.
Good. So minus 7. So now you got your x's on one side, your numbers on the other side.
And then you take the plus 1.
Divide by negative 1.
16.
So what does this really say? This is only true if x is 16. That's what that really says. So this is saying this is only true if 4 equals 2. Okay, no solution. This is only true if 2 equals... That's always true, so all freaking real numbers work there. That's how those three situations work. This is the one we're used to, and this is the freaky one, but this is more real life. In real life, there are just no answers to some situations. That's beautiful. You set up the math for a problem with no answer, the math is going to have no answer. Math is trying to tell you no. Yeah.
I subtracted the x.
Sure, yeah, that'll work. So instead of getting negatives, you got positives at the end, right? That's beautiful. I love it.
X equals 8.
Personally, I always do it so that my variables stay positive. So I would have subtracted x also. And you would have you should have gotten 16 at the end. So if you subtract x first, oops, got it. And then add 9, you should get 16 equals x. Same thing. Yeah, either way. I like it. I like it. What about inequalities? Stuff like let's see. By the way, this is not the way the whole class is going to go. I'm going to go pretty quick through this first piece. I'm not going to do this every single section. Bam, 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 bam. Inequalities. First off, how do you graph that? What do I put here? At least 17. Maybe a couple other things sitting around there. On the 17 goes what? Yeah, let me make sure. What did this book do? Well, this book doesn't do anything yet. There it is. Good. All right. So normally you would put an open circle here, right? So we need to get used to, if I want to put an open circle, you put a parenthesis there. And it has to do with, do you want to include the thing or not? Right? So here, do I want to include the 17? X greater than 17. So is 17 greater than 17? No, so I don't want to include the 17. That's why you would normally put an open circle here. You would shade it if you wanted to include it with me. So here I'm actually going to put a parenthesis. And then which way am I going to shade?
Right.
Yeah, up. So anybody ever heard of interval notation? Yes. The funny thing is, you just put, what do I go from to? I go from 17 to infinity. Then you put the same symbol on there. Infinity looks funky. Always open, I love it. Because the other option is, what if I would have had this instead? What would have been different? Good. If you want to put a closed circle, that means you want to include it. Include. If you want to include something, you use the bracket. Bracket looks like part of an I. It's the best I can come up with. Sorry. So then you would put a bracket on there. That means include the 17. And I still want to shade up. And then your interval notation would be from 17 to infinity still, but now it's include 17. Infinity never has the bracket because you can never get to it. You can't include it unless you can get to it. If you get to infinity, then you have reached nirvana or something. You got to tell me about that. Because you can still talk to me on this plane. I have energy now, John. So, and I also love it when people put infinity on the number line. That's cool. You basically found it, and then I'm like, okay, what's that? That's, I don't know what that is. I was going to say Buzz Lightyear, but okay. And one last little thing. We are going to review factoring. And I've actually got a cool little handout that I made a while back from my Math 90 students. I'm going to give it to you guys too. That spells out all the different forms of factoring. But before that is graphing. And we will start with a little review of, lines and slopes and intercepts and stuff like that. So we'll start off there next time. That, I think, is plenty for today.
This is oh yeah, so this is online.
Yeah, exactly. Good. No problem, man.
I have a question.
Yes.
Is this box